Due to backwards compatibility, C++ will never become any simpler, but the way that we use it can. Welcome back everyone, I'm James Murphy, and today we're talking about the simplest smart pointer in C++, unique pointer. This is a dumb pointer, otherwise known as a raw pointer or just a pointer. But this is a smart pointer, so what makes it so smart? Smart pointers are just wrappers around regular old pointers that help you prevent very common bugs. Namely, forgetting to delete a pointer and causing a memory leak, or accidentally deleting a pointer twice or in the wrong way. They can be used in a similar way to normal pointers, and they automate away some of the manual process causing some of the most common bugs. Let's take a look at a specific example. We have a vector of pointers to widgets, where each widget is allocated on the heap using new. We're using a vector of pointers instead of a vector of actual widgets because we're imagining there might be some kind of inheritance hierarchy going on. In actuality, we just have a single widget class. It just stores an integer and prints something on construction or destruction. Let's also suppose we've already written code using raw pointers or raw references. In this case, we're just printing something from the widget. Getting back to our example, we have a pretty typical workflow. We create our vector and push 5 widgets onto it. Then we loop over them and do some work. Maybe the user closes a widget, so we pop that one off and delete it. Or maybe we peel some of the widgets off and do some different work with it. Once we're done with that one, we delete it. At the end, we loop over the vector and delete all the remaining widgets. This code works, but it is very, very error-prone. Let's take a look at just a few of the ways this could have gone wrong. First, we're calling new in a loop. If the first new succeeds, but the second one throws an exception, then we just leak the first one. To handle that case without smart pointers, you'd need something like a try except and or go to fail. No real issues just looping through and using the widgets though. But in this case, say a widget is closed, it's very easy to forget to delete it. This is one of the most common ways that memory is leaked. Most likely nothing will go wrong with your program if you forget to delete this pointer. You've just got a very, very tiny memory leak. This case is even easier to forget because the delete has to be after the use. And of course, if all the widgets are closed, it's very easy to forget to delete all of them. Or instead of forgetting to delete the widget, you might forget to pop the widget, in which case you'll accidentally delete it a second time when you loop through the vector at the end. Deleting a pointer twice is undefined behavior, so if you do this even once on accident anywhere in your program, the entire program is undefined. This could result in a seg fault, garbage data being displayed to your user, or worse, a silent wrong answer in a calculation. The idea behind smart pointers is to make ownership of the pointer explicit. An owner of a pointer is an object that's responsible for deleting the pointer. So a unique pointer models an object that has exactly one owner at any given time. You could transfer or give up ownership, but when a unique pointer is destroyed, it's responsible for deleting whatever it owns. This completely gets rid of any confusion about when, where, or who's in charge of deleting a pointer. The way we clean up this example is by using a vector of unique pointers instead of a vector of raw pointers. So here we're using a unique pointer to widget instead of a pointer to widget. Here you can push back unique pointers instead of raw pointers. You can construct a unique pointer yourself, passing in a new widget. But for reasons beyond the scope of this video, the factory function makeUnique is a better alternative. All makeUnique does is make a unique pointer by calling new widget and forwarding all the arguments that you passed in. For type safety reasons, unique pointer will not automatically convert to a function expecting a pointer. Instead, you can use the get function to access the underlying pointer. Alternatively, if the code that you've already written was using references, the dereference operator works with smart pointers. Dereferencing the smart pointer will dereference its underlying pointer. So if you were passing everything by reference and you weren't using pointers in the first place, then your calling code doesn't need to change at all. In any case, whether using references or pointers, this is the recommended thing to do. It's not recommended to rewrite functions to take unique pointers instead of pointers. Only the code that dealt with creating new widgets or deleting widgets would need to be changed to use smart pointers. All of the code in the middle that just uses widget pointers or references shouldn't need to change. Then we get to another benefit. We no longer have to remember to delete this widget before popping it off the back. Popping off a unique pointer will automatically delete the resource. In the second case, the compiler automatically stops us from making a potential mistake. The compiler now forces us to move into this local variable last instead of copying into it. This might seem a bit annoying, but it actually protects you from the possibility of double deleting like we had in the raw pointer situation. You can use the arrow operator on a unique pointer just like you would a normal pointer. And finally, we don't need to do any of these deletes. The unique pointers handle that for us. So overall, the code got a little bit shorter, but the main benefit is that we just don't have to worry about news and deletes anymore. Why burden yourself with that when the compiler can do it for you? And this is where a lot of other tutorials might end. You see some flashy code fixing one example in a specific case. Someone that you don't really know tells you to use this thing that you don't really understand. But maybe you're super vigilant and you at least try to look at the source code and see how it works. So you go to definition and you see this, and then you never use unique pointer. Standard library implementers have to write it this way for reasons that unfortunately force the code to be completely unreadable. But the main ideas behind unique pointer are very simple and you could write it yourself. So let's do it. Let's write unique pointer. We'll start with the class template. For now, just assume that T is a normal, non-array, non-reference type. Think an int or a widget. The real standard unique pointer has a specialization for arrays, and it also allows you to specify a custom deleter type. But we're just going to keep it simple. No arrays and just using the built-in delete. Maybe we can add custom deleters in a follow-up video. A unique pointer just wraps a pointer, so let's give it a pointer member. The main feature of unique pointer is that it calls delete in its destructor. By putting delete in the destructor, we ensure that the pointer is eventually deleted because C++ guarantees that destructors are called even if there's an exception. Technically speaking, it's okay to delete a null pointer, which is going to be our not holding anything value, but I'm setting us up for custom deleters in the future, and a custom deleter might not support that. That's why we have this if check. Next, we need constructors. The real unique pointer has a ton of them, but you really only need just a few. We'll have one to construct from a raw pointer that just initializes our pointer to that value, and a default constructor to hold a null pointer. Now, it's common to have a copy constructor and a copy assignment operator to go along with it that make copies of your object, but for a unique pointer, that doesn't make sense. If we made a copy of a unique pointer, then we'd have two unique pointers that both think they own the same object and would both try to delete it. That would be incorrect. Unique ownership implies that copying a unique pointer would be a bug. So in this case, we explicitly delete the copy constructor and copy assignment operator. Next, let's define functions for either giving up or changing ownership. First up is release, which is for giving up ownership. We set our internal pointer to null, and then return the old one. We don't delete the old one. Giving up ownership means that the caller is taking that responsibility. It's their problem now. Also note that this pattern of setting a value and returning the old one is extremely common, and it can be written this way using standard exchange. Reset, on the other hand, swaps out the thing that we own. There's no one else that's taking that responsibility. We still own the old one. So after we take ownership of the new pointer, we need to delete the old one. And once again, this could be written using standard exchange. So release and reset are kind of the building blocks that we use to change ownership. But so far, we don't have an easy way to directly transfer ownership from one unique pointer to another. That's what the move constructor and move assignment operator are for. These operators are characterized by the fact that their function argument is an R-value reference. I'm definitely not going to attempt to explain value categories in the middle of another video. Suffice it to say that R-value references are typically temporaries or otherwise about to be destroyed. Think of a function's return value or something explicitly cast to R-value using standard move. The whole purpose of this is to allow you to steal the guts of another object before it's destroyed. In our case, stealing the guts of another unique pointer means asking it to release ownership of its held pointer and then assigning that to ourselves. Move assignment is similar. We guard against assigning to ourselves, ask the other thing to release ownership, and then take ownership for ourselves using reset. We need to use reset here instead of just assigning the pointer because we might already own something that needs to be deleted before we take ownership of something new. And that's basically it. We just need to define some getters and other convenience functions to make this usable like a normal pointer. Operator bool allows us to do if checks and other Boolean-like things on the pointer. The get function just gives out the underlying pointer so that people that don't care about ownership can just use it. Operator arrow allows us to forward arrow operations down to the underlying pointer so that p arrow something will result in m pointer arrow something. And finally, there's operator star, or the dereference operator if you prefer. It allows $P on the unique pointer to end up dereferencing the held pointer. Zooming out, the whole thing fit in under 50 lines of pretty easy code. And if you ignore blank lines, I can even sneak in make unique too. Okay, I'll zoom in on that for a sec, but this is just icing on the cake. Just change standard unique pointer to unique pointer and standard make unique to R make unique, and the whole thing works as is. It doesn't matter if an exception's thrown, our use widget function didn't have to change, we don't have to remember to manually delete anything. If we tried to break unique ownership by copying, the compiler would stop us. I mean, it's not like a great error message. C++ could definitely use some improvement on that front, but it does stop us. It forces us to use move, in which case ownership is transferred gracefully, and we don't have to loop over the vector and clean up at the end. All that's just taken care of. Now, of course, smart pointers are not a silver bullet. They are but one tool in your bag. It's possible that unique ownership does not fit your problem, although maybe shared ownership and a shared pointer would be a better fit. But even then, maybe not. It's possible to accidentally try to use a moved from object, and it's possible that one of your functions tries to keep a reference that becomes a dangling reference once the unique pointer goes out of scope. So using a unique pointer doesn't automatically protect you or make your code correct. However, the benefit of smart pointers is clear. Smart pointers reduce the number of bugs that you write. And unless you have a good reason not to, and there are some good reasons, then you probably should be using them. As always, thanks for watching, and thank you to my patrons and donors for supporting me. Don't forget to like, comment, subscribe, and if you especially liked the video, please consider becoming a patron on Patreon. Feel free to make suggestions of other video topics you'd like to hear about in the comments below. And you can also come and discuss programming in my Discord, link below. Anyway, thanks for watching, and see you next time.